Okay, little man, I've come to tuck you in. It's bedtime.
Dad, can you tell me a bedtime story, please?
Okay, buddy. What do you want to listen to?
Can you tell me about when you were a professor?
I guess you're old enough to hear that story now. So it all started in 1986, Princeton University. Okay, class. Today we are just going to be doing a review for the upcoming physics midterm, so I will leave the class up to questions that you may have. Yeah, what's your question?
Yeah, can you do chapter 8, question 9, please?
Can you read it for me?
Yeah. A light, rigid rod is 77 centimeters long. Its top end is pivoted on a frictionless horizontal axle. The rod hangs straight down at rest with a small, massive ball attached to the bottom end. You strike the ball, suddenly giving it a horizontal velocity so that it swings around in a full circle. What minimum speed at the bottom is required to make the ball go over the top of the circle?
Alright, so we will be doing chapter 8, question 9. So, as it was stated in the question, the length from the horizontal axis to the ball is about 77 centimeters, which means that it does a full rotation. The height is going to be 152 centimeters, or 1.52 meters. So, with that, we know that the potential energy is going to equal to the mass times gravity times the height. So we know that it's m times 9.8 times 1.52, or m times 15.092. Now, with that, we're going to move on to the next step. So at the top of the full rotation, we know that the potential energy is going to be what we just found out, and then the kinetic energy is going to be 0. So the kinetic energy is going to start, the initial kinetic energy, when the potential energy is going to finish. So our final potential energy is going to equal to our kinetic energy initial. So we know that our potential energy is going to be m times 15.092, which is going to equal to 1/2 mass times your velocity squared. So when we rearrange it, we're going to get v squared equals 2 times 15.092. V squared is equal to 30.194, or v equals 5.49 meters per second. And that's going to be your answer. Any other questions? Yeah.
Chapter 9, question 61, please.
Can you read it for me?
A garden hose is held as shown in figure P9.61. The hose is originally full of motionless water. What additional force is necessary to hold the nozzle stationary after the water flow is turned on if the discharge rate is 0.600 kilograms per second with a speed of 25 meters per second?
So now let's move on to chapter 9, question 61. So as stated in the question, our mass is going to be 0.6 kilograms per second, and then our speed is going to be 25 meters per second. Now this question is actually very simple because we're just going to use our equation that we know, force equals mass times acceleration. So it's going to be 0.6 kilograms per second times 25 meters per second, which is just going to equal 15 newtons. And that's our answer. Yeah.
Can you do chapter 10, number 52, please?
Can you read it for me?
Why is the following situation impossible? In a large city with an air pollution problem, a bus has no combustion engine. It runs over its citywide route on energy drawn from a large, rapidly rotating flywheel under the wheel of the floor of the bus. The flywheel is spun up to its maximum rotation rate of 300 revs per minute by an electric motor at the bus terminal. Every time the bus speeds up, the flywheel slows down slightly. The bus is equipped with regenerative braking so that the flywheel can speed up when the bus slows down. The flywheel is a uniform solid cylinder with mass 1,200 kilograms and a radius of 0.5 meters. The bus body does work against air resistance and rolling resistance at the average rate of 25 horsepower as it travels its route with an average speed of 35 kilometers per hour.
Chapter 10, question 52. So this question is asking why is the following situation possible? So with all the information given in the question, let's just convert it to stuff that we need. So we're going to first start with our angular speed. We are given 3,000 revs per minute. So we're going to convert that to radians, and that is 2 pi radians per 1 rev. And then we're going to convert the minutes to seconds, and it's 1 minute per 60 seconds. So we know that that's going to be 314.16 radians per second. Now for our average speed of v, we're given 35 kilometers per hour. So we're going to convert the kilometers to meters, and that's going to be 1,000 meters per kilometer. And then we're going to convert hours to seconds, and that's 1 hour per 3,600 seconds. And then we're given 9.72 meters per second. So now we're going to move on to power. We're given 25 horsepower, and we're going to convert it to watts. So per 1 horsepower is going to be 746 watts. So we're going to get 18,650 watts. And now when we have all this, we can calculate the moment of inertia. And the moment of inertia is going to mean inertia equals 1/2 times our mass times our radius squared, which equals 1/2 times 1,200 kilograms times 0.5 meters squared. And that means our moment of inertia is going to be 150 kilograms per meter squared. Okay, so let's continue. We're going to have all the values that we just found up in the top corner. So now we're going to have to find the rotational energy, and we know that equals 1/2 times inertia times our W that we found earlier squared. So it's going to equal 1/2 150 kilograms per meter squared times 314.16 radians per second, and then square that. So we're going to get 7,404,123 joules. So now that we have that, we can move on to our output power. And we know that the power equals the energy of rotation divided by time, which we know, and the energy of rotation, we can turn time into the position times this divided by the speed. So we're looking for this position right here. So when we rearrange everything, we know it's the energy of rotation times our speed divided by the total power. And we have all that from up above. So it's going to be 7,404,123 joules times 9.72 meters per second divided by 18,650 watts. And we're going to get 3.86 kilometers as our total distance that our power can travel. Now, why is this impossible? We know that this is impossible because the bus body works against our air resistance and our rolling resistance. This means that not enough energy is gained going downhill to make up for the energy used going uphill. And with a bus in a city, we need that. So that's why it's impossible. Okay, we probably have time for one more question. Yeah.
Can you do chapter 11, number 22, please?
Can you read that for me?
A uniform solid sphere of radius r equals 0.500 meters and mass of m equals 15.0 kilograms turns counterclockwise about a vertical axis through its center. Find its vector angular momentum about the axis with the angular speed of 3.00 radians per second.
All right, chapter 11, question 22. So we're going to write down everything that we're given. We're going to know that our radius is 0.5 meters, our mass is 15 kilograms, and our W is 3 radians per second. So our moment of inertia of a sphere equation is going to be 2/5 times our mass times radius squared. We just plug that in. It's going to be 2/5 times our 15 kilograms times 0.5 meters, and then square that. So we're going to get 1.5 kilograms per meter squared. Once we have that, we can move on to our angular momentum, which we know is going to be our moment of inertia times our W. So it's just going to be 1.5 kilograms meters squared times 3 radians per second to get 4.5 kilograms times meters squared divided by seconds, and then that's going to be our final answer. Oh. All right, looks like I'll see you next time. Don't forget to do your homework.
Unfortunately, I never got to see how well my students did on their midterm. I got arrested that night for tax evasion and selling an off-brand Thin Mints on the black market. Well, good night. I'll see you tomorrow.